All right, today we are going deep, I mean miles deep underground to solve what is, no exaggeration, a billion-dollar mystery. How on earth do you figure out what's inside an energy reservoir when you can't see it, you can't touch it, and the financial stakes are just astronomical?
This right here is the question for every reservoir engineer. You get the answer right, and we're talking about efficient production, huge profits. But get it wrong? Oh, that can lead to incredibly costly mistakes, equipment failures, and completely miscalculating the value of an entire oil field. So, how do they do it?
Okay, so let's jump into the first, and by far the fastest way to tackle this. It's called the correlation method. And really, you can think of it as making a highly educated guess based on what we've seen happen before. At its core, a correlation is basically a rule of thumb. It's a set of equations that were built using a ton of historical data from other oil fields. The logic is pretty simple, right? If your new reservoir is in a region and it looks a lot like an older one that's been studied to death, then maybe, just maybe, the fluid inside will behave in a similar way. But this method gives you a classic trade-off. On the one hand, you get instant answers and they cost you nothing. I mean, for an engineer who just needs a quick number, that's incredibly tempting. The downside, though, is huge. It's a massive gamble on accuracy. You're literally betting billions of dollars that your brand new reservoir is a perfect twin of one that was studied decades ago.
And to really understand the gamble, just look at where these famous correlations even come from. The standing correlation? That's based on crudes from California. GLASO is built on data from the North Sea. So if you're drilling in a totally new part of the world, how confident are you really that your fluid's going to behave like one of these? The less similar they are, the riskier that guess becomes.
But here's the real knockout blow for this method. A reservoir isn't some static swimming pool. As you produce from it, the pressure drops, and the fluid's properties change, sometimes dramatically. Correlations just give you a single snapshot in time. They simply can't predict how that fluid is going to evolve, which is, absolutely essential for planning production over the next 20 or 30 years. So that massive flaw leads us straight to our next solution, a huge technological leap forward called the Fluid Properties Estimator, or FPE. This is like bringing a powerful, miniaturized lab right to the well site. This quote from the source material just sums it up perfectly. The FPE was designed to solve that engineer's dilemma we were just talking about. The whole goal is to give you the best of both worlds. You get the near-instant results you love from correlations, but with an accuracy that gets really, really close to what you'd get from a full-blown, dedicated lab. So how does this thing actually work? Well, it's a pretty slick four-step process. First, you grab a fresh sample of the fluid right from the well. Second, you use some portable equipment right there on site to take a few key measurements. Third, and this is the really clever part, you feed those measurements into a thermodynamic computer model to tune it, to calibrate it to your specific fluid. And finally, that tuned model spits out all the detailed data you could possibly need. Okay, but does it work? Let's look at the numbers. For something called bubble point pressure, that's the critical point where gas starts to break out of the oil, the expected variance is just 0 to 3%. That is in an incredibly small margin of error for such a vital parameter. And it gets even better. For the oil volume factor, which is the metric that directly translates into how many billions of dollars worth of oil are in the ground, the variance is between 0 and 1%. I mean, getting that number right is absolutely critical, and this level of accuracy on site is just phenomenal.
And here is the real kicker. The entire process, from grabbing the sample to having a full report in your hands, takes less than 3 hours. You get high accuracy data fast enough to make critical decisions about that well right then and there.
But, sometimes highly accurate isn't enough. For the biggest, most important decisions, you need absolute certainty. And for that, you have to go to the gold standard, a full, comprehensive laboratory analysis. This is the ground truth. The heart of a lab analysis is what's called compositional analysis. This is where scientists use these really advanced techniques like gas chromatography to break the fluid down into its fundamental chemical building blocks. We're not just talking about pressure and volume anymore. This is about figuring out the fluid's exact chemical recipe. It's basically a DNA test for crude oil.
And why does that recipe matter so much? Well, because it answers the most critical long-term questions. First, what can we actually make from this oil? Is it light and sweet, perfect for gasoline? Or is it heavy and sour? That dictates its value. Second, is there anything nasty in there, like corrosive compounds that could literally eat through billion-dollar pipelines? And third, This detailed data is the only thing you can feed into powerful reservoir simulators to accurately predict how this thing is going to behave for decades. So this brings us right back to that central challenge for every engineer in the field. It's a classic dilemma, right? It's the need for speed versus the demand for absolute certainty. Each method we've talked about is a tool, and the real key is knowing which tool to use for the job at hand.
And this summary table lays it all out just perfectly. You've got correlations, they're instant, but they're risky. Great for a very early ballpark estimate. Then you have the FPE, fast and highly accurate, the perfect tool for making those operational decisions at the well site. And finally, the full lab analysis. It's slow, yeah, taking days or even weeks, but it provides the highest possible accuracy. It's totally non-negotiable for making those final investment decisions and planning for safety over the long haul.
And that leaves us with one final thought. From the quick guess to the on-site lab to the definitive analysis, each step gives you more certainty, but at the cost of time. And it brings us right back to that core dilemma and the question every engineer has to answer. When the stakes are worth billions of dollars, is fast enough ever really good enough?